Good afternoon, everyone. I'm happy to join you virtually today to discuss the Horizon Europe SNS project 6G-PATH and our ongoing work within the European 6G landscape. 6G-PATH is where theoretical research meets real-world application, and I'm excited to share our progress with you. Let me start with a quick introduction. I am Mohammad Rajiullah, a senior lecturer in the Department of Computer Science at Karlstad University. It's a mid-sized university in Sweden. In the background, you can see part of our beautiful campus. My research focuses on networking, especially 5G and 6G, non-terrestrial networks, IoT, also involved in network performance measurements, and also doing immersive media streaming. A key part in our work is understanding how advanced network capabilities can improve user experience, particularly in areas such as remote education and smart healthcare. To understand the path to IMT 2030 and through 6G, we first need to look at the broader 6G vision. 6G is not only about faster connectivity, it is about supporting a world where billions of connected devices, humans, vehicles, robots, and drones generate enormous volumes of digital information. It also reflects a major shift in focus from purely human-centric networks to systems that support both human and machine-centric communication. To enable this, 6G will require a much more flexible architecture, often described as a network of networks, integrating terrestrial and non-terrestrial communications together with joint sensing capabilities. And finally, AI and machine learning will play a central role in making these networks efficient, adaptive, and increasingly automated through zero-touch operation. To understand 6G-PATH, we first need to look at the broader framework in which it operates. The Smart Networks and Services Joint Undertaking, or SNS JU. SNS JU is a partnership between the European Commission and European industry created to strengthen Europe's leadership in next-generation communication networks and services. This slide shows the strategic mission of SNS JU and how that mission is translated into action. On the left, you see the strategic mission of SNS JU, which is to secure Europe's digital sovereignty in the digital age. In other words, Europe aims to develop and deploy future communication technologies in a competitive, trustworthy, and independent way. In the middle, this is reflected in the dual mission. On one side, 6G innovation, which looks at future technologies and breakthrough ideas. And on the other side, 5G deployment and market validation, which uses existing beyond 5G infrastructure to solve real-world problems today. On the right, we see the operational pipeline. Streams A and B focus on core technologies and future innovation. Stream C provides an experimental sandbox, and Stream D is where large-scale trials and pilots take place. This is where 6G-PATH fits. Its role is to bridge the gap between theoretical 6G research and practical market deployment by validating technologies in real-world environments. Now let's look specifically at 6G-PATH. The full project name is 6G Pilots and Trials Through Europe. This is a StreamD project that is designed to bridge the gap between 6G research and commercial reality. We are a consortium of 29 partners ranging from operators such as Telefonica to academic institutions such as our Karlstad University. Together, we are running 10 large-scale use cases across 7 European testbeds hosted by our partners. Our goal is twofold. We are measuring KPIs to ensure the technical infrastructure performs as expected, but we are also measuring key value indicators or KVIs. That means we are also looking at sustainability, inclusivity, and real human benefit across our 4 target verticals, which are farming, education, health, and smart cities. One other important thing here is that 6G-PATH is an open project. Through open calls, we also bring external innovators into the ecosystem to test their solutions on our infrastructure. To guide this work, the project is organized around 7 strategic objectives. At a high level, these objectives cover 3 areas. First, building the foundation by establishing beyond 5G and 6G experimental testbeds and a common integration platform. Second, executing large-scale validation through our internal use cases and external experiments brought in through the open calls, as I mentioned before. And third, creating long-term impact by supporting commercialization, contributing to standardization, and making knowledge openly available for the wider European SNS ecosystem. So overall, these objectives take us from infrastructure setup to real-world trials and finally to lasting impact beyond the project itself. So this slide gives an overview of the 6G-PATH partners who are hosting Beyond 5G testbeds across Europe. Each of these sites plays a role in the project's broader experimentation and validation activities. And of course, given the time available, I will narrow the focus and briefly highlight the Karlstad University testbed in Sweden. This slide gives an overview of the Beyond 5G testbed at Karlstad University. It's a flexible experimental platform and it is designed for testing advanced mobile network technologies in a real campus environment. The testbed provides both indoor and outdoor connectivity across the campus. On the left, you can see the indoor setup, which includes support for local network functions such as local breakout and edge support. And these are important because they help reduce latency and improve responsiveness for demanding applications. On the right, the slide highlights the key capabilities of the platform. It supports 5G SA, NSA, and 4G. And also it supports network slicing, L4S, and many other advanced connectivity options such as Starlink and RedCap. Altogether, these features make the testbed versatile enough to support many different use cases and deployment scenarios. And most importantly, this is not just a lab-based setup. The platform is validated through real-world campus trials. And it helps to bridge the gap between technical experimentation and practical deployment that we are doing in 6G-PATH project. Next, let's briefly look at the different use cases being implemented across the 6G-PATH testbeds, and these are organized into four main verticals: farming, education, health, and smart cities. I will now go through them one by one, but briefly. Let's start with smart farming. At the La Mayora station in Spain, we are conducting trials that address Mediterranean water scarcity. The core of UC Farm 1 is a shift from static irrigation to autonomous AI-driven water management. And what makes this a true 6G trial is the simultaneous use of three different network slices: MMTC for soil sensors, URLLC for precision drone control, and EMBB for the analysis of 4K drone video. And all of these are running in the same infrastructure. By deploying application functions at the edge, we process large volumes of multi-spectrum data locally, and this allows the system to detect crop stress and adjust irrigation in real time. And ultimately, it helps reduce water use and operational cost for farmers. Moving to the educational vertical, 6G-PATH is tackling distinct challenges here. First, in Romania, through UC Edu1, we focus on social inclusivity. We use 6G's ultra-high bandwidth to deliver immersive XR content to rural schools. The idea is to ensure that a student's location doesn't limit access to high-quality digital learning. At the same time, in the UK, through UC Edu2, we are building the classroom of the future. Here, 6G is used to address a pedagogical challenge, the complexity of explaining virtual networks to the students. By using holographic and haptic interfaces, students can actually see and manipulate 6G topologies in a 3D environment. Across both trials, we are pursuing we are pushing the limits of the network. We are validating throughputs above 1.5 gigabit per second. We are leveraging edge cloud processing for sustaining low latency communications with a very low jitter value of 5 milliseconds, and this is essential for immersive and responsive XR experiences. Next, we move to our third use case in the educational vertical, and it is led by Karlstad University in Sweden. This trial addresses a major bottleneck in healthcare training. Today, pre-hospital nurses often train using medical mannequins that are physically tied to classroom infrastructure. This limits training to static lab environments. it doesn't fully reflect the pressure and mobility of real emergencies. So in this use case, we use beyond 5G or 6G technologies to free these trainings from fixed lab settings. By leveraging ultra low latency, instructors can remotely control the mannequin's physiological responses in real time while these mannequins are placed inside a moving ambulance or at a simulated accident scene. At the same time, we use high uplink capacity to stream 360-degree immersive video and head-mounted camera feeds back to the remote classroom from inside the ambulance or simulated accident scene. This allows a larger group of students to participate in a high fidelity field exercise from anywhere while also supporting academic equity and better preparation for real emergency response. Turning to the health vertical, we are validating how 6G can effectively move the hospital closer to the patient. In UC Health 1, we are testing 3D hydrogel patches. Imagine a nurse in a remote village using a nomadic micronetwork to create a high-resolution 3D scan of a complex wound from a patient. This data is then sent over 6G to a hospital where specialists can supervise the on-site printing of a customized medicated patch. In this way, patients in isolated areas can receive the same precision treatment as those in major cities. Moving to the next one, UC Health 2 focuses on elderly monitoring. Here we move beyond simple tracking toward AI-powered predictive care. By processing data from wearables and non-invasive sensors at the edge, we can automatically detect pain levels or fall risk. If a risk is identified, the system can trigger an immediate telehealth consultation with a doctor. Together, these use cases show how 6G can support a more resilient, proactive, and inclusive healthcare system. Our final vertical is smart cities, where 6G is integrated into the fabric of urban life. In UC City 1 in Aveiro, Portugal, we are building a sensing city. Here, 6G allows autonomous vehicles to exchange real-time data with city sensors. A particularly interesting aspect is dynamic edge replication, where the network service effectively follows the vehicle as it moves, and it helps to maintain very low latency for safety-critical operation. In UCCD2 in Spain, the focus is on automated logistics. We use 6G's high reliability to control automated guided vehicle or AGVs in industrial environments. The idea is to help removing human workers from hazardous heavy lifting tasks. And in UCCD3 in Greece, we focus on security coordination. We have developed a mission-critical platform that gives fast responders a secure and resilient real-time communication link, even in demanding emergency situations. Together, these trials show that 6G is not just about speed, it is about creating cities that are safer, more efficient, and better coordinated. Earlier, I mentioned that 6G-PATH is designed as an open project, and this is where that becomes concrete. Through its open calls, we are expanding the ecosystem beyond the core consortium. Through these calls, external SMEs and research teams are able to use our infrastructure to test their own 6G applications. This means that 6G-PATH is not only validating use cases from the core consortium, but also enabling much broader pan-European experimentation and innovation. To wrap up, I invite you to follow our progress as we help shape the future of connectivity. You can find more information, including project updates and trial results, on our website, 6gpath.eu. You can also follow 6G-PATH on X and LinkedIn for news and updates. And thank you all very much for your time.